Today we're going to learn about the ideal gas law. So the ideal gas law is made up of the equation PV equals N RT, with P being pressure, which we'll measure in ATM, V is volume, which we'll measure in L, or liters, N is moles, R is the gas constant, which for ATM is 0.0821, and T is temperature, which is measured in Kelvin. This equation assumes that there are no IMFs and that there is no volume. So an example problem for this could be 4 moles. Well, what's the pressure of 4 moles of H2 in 2.4 liters at 292 Kelvin. So if we plug that into the equation, then it would be PV equals N RT, with the pressure being unknown, the volume being 2.4, moles being 4, gas constant being 0.0821, and temperature being 292. And if we take 4.0821 and 292 divided by 2.4 for the volume, and we get the pressure, which is and pressure would be 39.96 atm. So for the ideal gas law, we have to figure out what deviates more. And deviations are based off of lower temperature, because that gives the molecules less energy to overcome IMFs, a higher pressure, because that gives molecules an increased strength in their IMFs, and a higher size, because that increases the volume that particles take up, which in turn lowers the volume given to them. And what about volume? Well, in this container, we're going to have no or little volume that the particles take up. So there's just going to be little dots. And then in this, it has volume. So they're larger, they're bigger in size, and in turn create more collisions with the sides of containers. So having volume gives it less entropy, which is randomness, and it lowers the volume, which in turn happens because of the increase in size. And what about order. So in this one, molecules are going around randomly, juvenile delinquently, hitting the containers wherever they please. And in this one, it's like the buddy system. Stick together. There's less random order. So it's not as random as without. It doesn't hit the containers as much. And in turn, increasing the IMF decreases pressure because it doesn't hit as much. So finally, we have an example problem, and that is which gas will deviate more or least, according to the ideal gas law. So out of the H2O2, xenon, and H2O, you can pause the video and find out which one will deviate more or least. What would deviate most is H2O because the polar properties make the IMF stronger, and therefore the molecules stick together, which means it bounces off the containers less, meaning the pressure is lowered. What deviates least is H2 because it has the smallest size and the weakest IMFs, which is London dispersion, making it the most ideal. And I hope you got that.